If you watched The Wiggles as a kid, then you have a head start when it comes to studying physics, where wiggling is commonplace.
One thing that all things have in common is that they love to wiggle, and these wiggles, or waves, are everywhere in our world, even if we might not see them.
Waves are caused by vibrations, and they occur when the medium of the wave, which could be sound, water, or anything you can think of, moves up and down because of a disturbance. All waves have amplitude, the height of the wave from the middle, and frequency, or how frequently the wave completes a cycle. Frequency is important because it correlates with pitch, but we'll talk more about that later. Although there are many types of waves, the specific type of wave we will be focusing on today is a standing wave. No, not those type of waves. Standing waves are waves that appear to be standing still rather than continuously moving in one direction as a transverse or longitudinal wave might. Standing waves occur because of wave reflection. The light blue wave is the original wave, a transverse wave, while the dark blue wave is its reflection. Think of the reflection and the original wave as two different waves. Sometimes the waves will line up and combine to create a more amplified wave. Other times, the waves will be offset so that they cancel each other out. What we end up seeing is a standing wave that results from these interferences. Two key points on these waves are the nodes and the antinodes. The nodes are the points on the standing wave that do not move, while the antinodes are the points on the standing wave that move the most.
This is a marimba, both a cool instrument and a great tool for showcasing standing waves and how physical characteristics can affect them.
A marimba consists of many wooden bars that have arches cut in them, called keys. Each key plays a different note, and we can find out how this happens using observation and the physics we just learned. In real time, it might not look like much, but when I disturb the key with the mallet, you can see in slow motion that the disturbance causes the wood to wiggle, and if you're thinking it's like a wave, you're absolutely right.
We can actually see the nodes of this standing wave using salt.
When I disturb the key with the mallet, the key vibrates, creating a standing wave. The wave will push the salt to the nodes where the standing wave does not vibrate, and that's how we can picture the nodal areas on a marimba key.
In order to create an instrument with a full range of pitches, we have to be able to manipulate the waves. All of these keys have different frequencies and therefore different pitches. For example, lower pitches have lower frequencies, meaning the key must vibrate slower. The frequency is determined by the length of the bar and the bar thickness at the center. These two physical characteristics determine the pitch of the note.
Bar thickness, however, has the most impact on the frequency of the note. It affects two things, flexural strength and mass. However, these two qualities have opposite effects on the wave. The reduction of flexural strength causes the wave to vibrate slower, but the reduction of mass causes the bar to vibrate faster. It's an all-out battle until we realize that flexural strength is proportional to the cube of bar thickness, while mass is only proportional to the bar thickness on its own. Flexural strength wins. This means that a decrease in bar thickness will lower the flexural strength more than it will the mass, resulting in a lower frequency. So overall, removing wood through the arch will lower the bar thickness, which will lower the frequency or the pitch. Who knew there was so much physics hiding in a marimba? Thanks for watching, and I hope you enjoyed learning a little bit about physics and the marimba.